techniques and all it uses, but it should be able to configure itself. Inventory management and all, it should happen. Maintenance management, all should happen in this system in dynamic way. That's the way we look into smart manufacturing. Now, coming to our role, how we are getting connected to this subject is because of our Government of India policy. They are looking into, there is in our ministry, Ministry of Heavy Industry, they have a scheme called Enhancement of Competitiveness of Indian Capital Goods Sector. So, basically, their main aim is to improve the GDP, manufacturing GDP basically, through manufacturing GDP. And people, our policymaker felt that this smart manufacturing industry 4.0 can improve the productivity, efficiencies, and all sort of thing. And so that we are able to, the contribution from manufacturing can be more in our GDP. That is a basic concept. That scheme is their Government of India scheme, and under our ministry. And there they started with creating a common engineering facility center and center of excellence all over India. So we are one of them. I think at Bangalore, and others are there. You can see that there initially these are the CEFC and COE spread over India. And what we do at CMTI, our main activities are, I think, again here, there. So we have set up a smart manufacturing, sort of workshop where we have tried to integrate design, and the production and the performance. All three main activities, core activities, which is part of manufacturing operations, we have combined, and we have created a physical smart manufacturing shop. Plus, also we have created digital twin of that. We'll discuss that. What is that later? Then we created a platform where development, testing, and validation of Industry 4.0 products and solutions can happen. That is the way we have done. And we have been developing, indigenously we are developing and rolling out a smart manufacturing solution which goes to our Indian manufacturing industry, including MSME. So that is the way we are doing. And of course, as the concepts are new and evolving, we have created a platform where we conduct a lot of programs, awareness program, training we call experimental learning, where you can people can hands-on, they can they can learn, and also they can also create their own use cases if they want to implement these techniques in their factory. So that's the way we do. And the same thing is represented here. We call our center, we call Smart Manufacturing Demonstration and Development Center, SMDDC in short. And then the thing is that if you see the activities, basically Industry 4.0 implementation has occurred in this, and that including a smart factory. These things are available, and using indigenous technology we have done our own technologies. And then also we are developing a lot of products and solutions with working with industry. We work with industry together in collaborative mode. We are developing solutions where the commercialization will take place through industry partner. So that's the way we are working. And of course, this training and all also we are conducting. So that was a brief about our activity. If you look into our smart factory, I think the left side you see the picture, outer, inner, and our control room. So that is there. The top picture shows you our smart metal working shop, and then the middle one shows you the inside view of that, and then this shows the monitoring and control room. So and the same thing is represented in animation. So if you see the component, that any item comes, it goes through predefined machines and all, and through automated systems like AMR and robots and all, it gets loaded to different machines and all, and then finally after it is the component is ready, it is metrology take place, and if everything is okay, then it goes to stores. So that's the way it works. And then you see all machines are connected to not to each other, also to the their server, common server, and master, and we can monitor all the activities through the master control room and all. So that is the way. And also we have integrated our smart metalworking operations through CAD, CAM, and sort of digital twin sort of concepts. So I have a small video. I just play. For it may run for 1.5 minutes. So if you have a look on.
Manufacturing Technology Institute has set up a smart manufacturing demo and development cell SMDDC as a common engineering facility center to develop, implement and support smart manufacturing and Industry 4.0 practices by Indian manufacturing industry. The The SMDDC has a 10,000 square feet smart metal working workshop, which has machines like HMC, VMC, TMC, turning machines supported by integrated smart metrology lab for inspection and quality control of components that are fabricated. The raw material or tools or any bought outs that are received for machining or operation of workshop is given a particular RFID code for usage tracking and monitoring purpose. IoT-enabled automated guided vehicle (AGV) with integrated robotic arm makes the raw material unloading and movement within the workshop with a predefined map built into it. The AGV's movement is controlled and monitored based on the material movement requirement. AGV places the material to the machining facilities as per the navigation route of process planning. IoT-enabled machine monitoring solutions are capable of reporting the real-time status of the machine operations and its health with analytics for improvement of productivity and efficiency. Apart from smart factory solutions, technology and product developed and integrated by CMTI like digital twin of spindle and feed drive systems of machine tools, integrated smart foundry 4.0, smart integrated spindle, etc., enriches the SMDDC capability. The outcomes are smart diagnosis and prognosis, smart inventory management, production analytics, and model-based control. An indispensable part of the IIoT to manage SMDDC factory is through cloud connectivity. Real-time data provides operational visibility of the factory. The SMDDC smart metrology equipments are capable of capturing real-world data through high-precision contact and non-contact inspections, while the metrology software provides actionable information through advanced analytics, reporting and reverse engineering. This IIoT-enabled smart factory has machine and data connections at the factory floor which extend well beyond to include the entire supply chain, from raw material to finished product.
So that was a sort of brief video about the working of our smart factory, and I will move on the next slide, please. Okay, yeah. So apart from that, for the benefit of other people who are working on this domain, being National Institute, we created sort of many experimental learning labs in the various technologies which are driving Industry 4.0. So like mechatronics and automation, industrial automation lab, CNC controls, smart condition monitoring lab, AR, VR, AI/ML, smart metrology. These are all concepts which are driving Industry 4.0. We have a separate lab which is basically we are using it for experimental learning, and also industry people, if they come there, they can not only they learn by practicing, also they can create their own use cases so that it can get into their system. That is the way we look into that now. So that was basically about our whatever we have done in as a part of smart factory. Now we will come to the technology development, because and I mentioned that the core theme of our center is to develop indigenous technology which are driving Industry 4.0, and that we are doing with almost all work either with the collaboration with industry, or we are doing the work which is sponsored by industry. That is the way. So that is the concept on which we are working, and we are developing the technology. So this is the first product which I wanted to tell you. As we are in machine tool, we have been working in machine tool. We are only R&D organization who was driving machine tool development. So we come out with the first concept to make a smart machine tool, which has multiple technologies running inside that. So when it comes to a machine tool, we went into to develop a ultra precision machine tool, and I will not get into that how to develop a ultra precision machine tool. It has got own design analysis and techniques to develop a ultra precision machine. Then over that we have added a lot of features which makes a truly smart machine. So if you see those features here, you will find like machine error compensation. So as any machine, I think you most of you understand that any machine as it moves and all, it will have errors, right? Like positioning error or thermoelastic errors sort of thing. So this type of errors occurs in machine, and that it should be able to, in real time, it should be able to map and compensate it. So that those are through adaptive control, so that as the operator operates the thing, it is in the background, these all compensation, the mapping of, mapping of error and compensation calculations, algorithms, they run behind the scenario, and it corrects. So you get better accuracies on these machines. That's the way we look into that. Other one is that machine, related to performance. So the machines is an instrumented machine. So we take all the, inputs coming from different sensors and all, and we try to monitor the health in real time. And also we are predicting what is going to go wrong. Because if you see, we are looking into the critical machine elements, which are subjected to, because of continuous movements and all, subjected to some wear and tear or some sort of assembly issue, integration issue, and because of that, some problems can occur. So we should be able to not only find out what is wrong, also we should try to see that when it is likely to create major problem for you, so that there is a sort of breakdown. So that's called something concepts on predictive analytics. So based on that, we are able to find out what is going to happen in coming future. As machine tool consists not only of machine elements, also consists of cutting tool. So that also we can do monitoring. Means what is the status of cutting tool, wear and sort of thing we can find out. And life of tool also we can predict. Again, you have to use AI/ML techniques, and you have to do you have to predict the remaining useful life. That is the way we work. And not only that, even coming to the process also we are monitoring. Like, if this is a turning machine, right? So as the turning take place, so we monitor the process. Apart from machine, we are monitoring the processes, and we are identifying the problems connected with the processes, and also what is the likely outcome of these problems, and what is finally you are looking from machine a component, right? So the components has quality parameters, so it will tell you whether that quality parameters tolerances it is going to meet or not. So that is the way we are looking into the machine. We have displayed this machine in our international machine tool exhibition, and we got award and all. And later we have transferred this technology to one of the biggest machine tool OEM of our country, that is ACE Group, ACE Micromatic Group. So that is the thing we want to tell you. So I just to tell you one thing, because to how we do actually. Let us take the one case like real-time thermal error compensation machine tool using AI/ML. So what we do actually, initially, as you know, that all machine learning techniques based on some data, you have to collect conduct lot of experiment, collect lot of data. So the data you have to collect to see, in case of if you want to compensate thermoelastic errors, you should know what is the temperature maps at different working condition and what is the deformation. So this you can do only by experiment. So we have done lot of experiment, collected lot of data, where we have it is one side we have thermal map and other side deformations. Then we are feeding into your algorithms, which is for AI/ML based, machine learning based, and then we are predicting the likely the deformations which can occur based on the temperature distribution on the machine, right? So once we know that, then we have to write another program, and as it is occurring based on the positions and based on the temperature of the machine, it can correct through its own control system. So that is all about this, you can see. And these are the practical cases. So you can see that the total error over a shift, in machine around 50 micrometer, which after this implementation, we can bring it to 3 micrometer band. So that is there. So this thing. So likewise, we have developed other types of machines also, which are smart. So another concept is that smart foundry. I think foundry, sand-based foundry, system, which consists of pattern making using 3D printing, and then sand, mixing, and then mold making, and then metal casting, right? So there are different various machines are there, and which are used to do that. And conventionally, they are, they are not Industry 4.0 based systems and all. So we got a problem where we need to integrate so-called legacy foundry machine into a smart machine. So then we created some common interface where we are taking inputs from all the different machines, which are individual machines, 3D printer or sand mixing, mold making, and metal casting, and then all this information goes to a common place, and then from there we are, through the dashboards and all, we are able to monitor, and also we are able to control those machines from that common place. So that way we have demonstrated that legacy sort of machines can be also converted into smart machines. Then later we developed from fundamentals, from design, we developed a integrated smart foundry machines. Means whatever these subsystems are there, we have put into one system and we brought automation. Means from one station to other station it has to move. So this, considering this integration and automation, and with this concept, we created a complete integrated system where based on your component, the automatically 3D printing will occur, and then patterns are made. Then it moves to, then sand mixing takes place, and then it moves to the mold making. That molds are made, and mold moves to metal casting, and then all metal components are produced. And same time, you are able to monitor them. Not only monitor, you are able to control the process parameter of all these processes. So these are the power of Industry 4.0 and AI/ML. So next, you see, I think if you see every in our manufacturing shops, most of the machines are slightly old generations. Means they may be 20 years, 30 years old also, and they are working fine. So we develop certain technology where without and you cannot get data from the control system. It's not easy to from the old control system to get useful data where you can do analytics. So for those machines, we added few of the sensors and some edge devices we call, which is near to the machine. We can directly mount on the machine, and with that we are able to make them smart. You can see. So this is a 30 years old Majak machine, and then with this adding sensor and some edge devices, we are able to monitor temperature, vibration, pressure, and energy, and also using vision techniques, the components which are coming out, we are able to monitor the quality parameters, and also we are able to compare whether it is okay or not. So that is this we have done, and these are the why we have done, because these are the requirement of our Indian industry. Everywhere you find this type of scenario that is there. Then with other industry partner, we have developed a smart integrated motor spindle which can run at higher speed, and it is truly instrumented where from design we have looked into integration of the sensors and all different type of sensors, vibration, temperature and all, and then we have with this, if you want to use this spindle, you have to use one edge device where the sensor outputs will go, and from there it will do some analytics and all, and you can through dashboard you can see the performance of the machine of the spindle anywhere in the world. So OEMs can see, and even users also can see. So this is another example which we wanted to show you. The next example, what we have done, we created a digital twin of a machine tool. We have started working on that, and then what we did initially, the machine tool has two major components, subsystems, which is called slides as well as spindle. So what we have done, we created digital twin. Digital twin basically it is you have physical system and you have a CAD based simulation based model, which is a 3D model, and you need to connect them in real time and say that as it is working in real time, the information from the physical system, it is going to your digital 3D models, and the physics-based simulations, they are running in the real time. That is the way we look into that. I think for aerospace people, I need not to tell what is the importance of digital twin. So with this, you can do a lot of things. You can find out the useful life or problems in the real time, which is occurring on your machine more correctly. As well as you can do some accelerated tests. Instead of doing on physical system, you can do in digital system. So it is not like a pure 3D CAD model. It is basically a connected model with your physical system, where that your real-time simulations are running. Basically based on, also it is taking inputs from your physical system. So that is the way it works. So it is much more accurate. In real time, it can predict the likely problems and the failures which are going to occur, residual lives, as well as it also provides you a platform where you can do accelerated test. which you don't like to do on your physical system. You can directly do on digital twin. So this is the advantage of that. We have done this, this thing. And I think everywhere we have put industry partners, means we worked with industry partners also, and we have done that. Next is that this establishment of this, that smart metalworking shop, which you have already seen. There also we worked with industry partner, Hexagon, and we have developed our own technology, indigenous technologies and all. Including, we have also developed IoT platforms. Actually, our own platform, we are working with industry. They're all indigenous products, where this IoT framework, anybody can use that, and it can connect their machines and all, and can monitor the machines. So these are indigenous products. Likewise, for MSME, they require low-cost solutions, right? So in that, we have looked into how to help MSME who has to spend a small amount of money and make their shops smart. We have come out with low-cost solutions, like low-cost energy monitoring solutions, where they have to, we are providing them sensor and also edge devices and the dashboards, so that they can, they can install, and something like a plug and play. They can convert the legacy or old machines into smart machines. So this is some of the things I think it is shown here, and then. So in that, even I think energy monitoring is one of the solution which is required by a lot of industry. So this smart energy meters are already available from OEMs and all, other MNCs and all. So we have developed, we have low cost energy meter we have developed, where we are providing a dashboard also where they can do analytics. So that's the way we looked into different things. Coming to AMR, I think at autonomous mobile robot development and all, we are working with industry partner, and we are coming out with development of indigenous AMR system, where this not only the software, even the hardware and all, together we are able to develop. So some of the work we have already done, like this coming to software, the SLAM and sort of thing, which is mapping as the AMR moves in the shop floor, it should know. It should be able to map the environment, so that it takes care of the obstacles and all, and then it moves on its own. Means it doesn't require sort of a fixed path. So that is the way these softwares are useful, and AMR development are useful. So we are doing this with industry partners. Right, in metal cutting again, if you look into sort of I think the people who are familiar with milling machines and all, we use a tool holder. So we try to make the tool holder smart, so that there is a metal cutting occurring, so we can monitor the process performance through those sensors mounted on that, and wirelessly these information are going to your server, and you can do analytics and find whether the processes, what you are doing, it is stable or not stable. So that's the way we have looked into that, that way. Coming to metrology, I think all people, when they make some component, they will have design, 2D design, and based on that components are made, and some quality assurance take place. So we have developed a software where the drawings, 2D drawings, it can read, and it can identify the critical parameters which needs to be monitored, and with the tolerances. And then the software also will help you to connect with the the metrology equipments and all, which has got Bluetooth and all. So as you keep on measuring certain parameters, it will go to the right place, and it will compare with the tolerance and say whether it is okay or not okay. So that is the thing. This is also indigenous development we have done. It's very useful, and we are working with many people to supply them to that. So this has that concept of auto ballooning. So as soon as a drawing comes, it will identify all these critical parameters, and it lists automatically and the tolerances, and it allows you to make measurements through some devices, physical devices, and the values will come, and it will compare, and also it will identify the which are exceeding, and it will also notify to the respective supervisor and all, and tell them that which is out of tolerance. So these are things. Coming back to that, for looking into the majority of machine where that condition monitoring is required, right? Machine tools require condition monitoring, and quite frequently, and people are looking for a solution which can give you something like a universal sort of thing, which can measure vibration, which can measure temperature, which can measure energy, right? So that way we created a small device which can collect the data from the sensors, which from the vibration, temperature, and energy, and which can be mounted directly on the machine. And then it can do some analytics, and also it can inform you what is through dashboard what is wrong, and if everything is okay and things are deteriorating, when it is going to be wrong. So that is a prediction, also prediction capability also it has. So likewise, we have also worked on AR, VR. I think augmented reality and virtual reality concepts, I think it is there in already in different domains. We try to adopt into manufacturing domain for different reasons. We can use it for training and sort of thing like training on operation of machines. We can use that. Also for machine maintenance, right? So, if you go near any machine and if you use your, air systems and you take a map, then it will start telling you that, what is inside and what is the condition of different elements, temperature, vibration and all. And also it will help you to interact. And if you want to pass some messages, you can do through that system. So that is the way maintenance also it is very useful, and training, and also we are using for prototyping. Like we are building some complex system, right? So that generally experts are required to build based on some instructions and all. Assembly, what you call plan or some quality plan, these all are required. They are generally, or you have to read through them, and some experts are required, skilled people are required to build system, right? So this you can create as AR experience, and then you can put, as soon as the person goes with HoloLens and all, it will start guiding him. That this is the component, over that this you have to keep another component, this much you have to tighten this all. So that is where it will help. And in case if you are doing a mistake, it will also tell you that you are doing a mistake. So these are the few of the solutions which we have done for the industry and all. So that is the thing we have shown. And we have also worked on digital twin and also holography. So digital twin you can present in different way, and we have tried to see that through holography techniques, 3D holography and digital twin concept, we have added together and brought some solutions and all. So some of the thing not only we have developed, you can see some of the solutions which we have done for the industry, that is also there, like for a company which is having a lot of welding equipments, right? So they are all legacy equipment. So they wanted to assure the quality. So, and they are all legacy, they are non-connected machines. So we have given a solution where, we are getting information from all the welding equipment, and also we are guiding them. Not only we are monitoring, we are also guiding them, what parameter to be set on for a particular component and all. So that is the way we have provided solution to GARB India. Likewise, other low-cost solution which is based on energy monitoring. This whatever products we develop, we implemented at industry, and they are getting benefited from that. We have also worked not only for small people, big people like Toyota and all. So you can see that 2 plants, we have implemented that, Industry 4.0 concepts. So you can see that TNG plant where that 65 machines, they wanted to monitor 17 parameters from each machine. So you can imagine. So this much we have created sort of system where all machines you can monitor, and every machine will have 17 parameters. So you can, any of the parameter, if it is going out of limit or something wrong, he will get notified, the respective person. And apart from the dashboard also you can see in red, you can see that in red and green. So if all green means everything is fine, and if something is red, you can get into that and you can do analytics. You can look into analytics, why it is wrong and all this thing we have done. So these are the physical implementation. This is another plant we have done. Implementation of this thing, smart manufacturing. So this was some use cases which I have tried to present to you. Apart from that, we have been working on skill development and training things also, which I wanted to tell you. So we are offering courses which is hands-on sort of training program, experimental learning in these all domains which are driving Industry 4.0, AI, ML, AR, VR, AMR, condition monitoring, pneumatics, hydraulics, mechatronics, PLC, and CNC, in all the areas. We have provisions where we can provide the training to people so that it is easy for them to understand and adopt this technology. So this, you can see, we have conducted so many, skill development programs, which is awareness program, and these are the numbers who got benefited. we call executive training programs for basically for engineers and officers from different industry. So like with internship we provide, we participate in exhibition and conferences. Also we present our activities and all. And apprentices programs also we run. And also we, in this domain we have programs on design innovation. We conduct some program where people can come, students and all, and they can try to build prototype with our mentorship. So that is the way we look into these events and all. And some of the summary of that, that whatever we have done, almost 15 plus solutions we have developed over the 3 to 4 years time, which we have, out of that 6 are basically with industry partners and 4 are sponsored by industry. So 6 together we have done and 4 we have done based on sponsorship from industry, and remaining 5 we have done on our own. So this way we have done. We have done technology transfers also at the end of this thing, and these are some of the pictures which is depicting our this thing. So now what we can do actually, how CMTI can work with industry or with people who are interested in the domain. So we can do technology and product development in collaboration with those industry partners, and there is a provision for government funding. So government scheme, under government scheme we can take industry or other agents, other institution, we can work together and bring the indigenous product, import substitution product in our country. So that's the way we work. Then also we can we provide whatever technology we have developed, right? So that we transfer to industry, and they can, in fact, they can make mass commercialization. So we do transfer of technology, whatever we have done. We don't want to keep anything with us, and we don't want to make money. That is, I think, similar concept. I think CSR laboratory is also working. So that way, I think you should understand. So that way, so that is the way we work, and we have actually being a national lab and test platform, testing and validation. Services we provide. So if anybody who is our competitor so-called or any other person startup, they have developed something and they want to test in our system, they are welcome. So we provide them help to test and validate their product in our modular smart factory system. So also we take 1:1. If somebody approaches, like you saw that Toyota and all, they approach, or maybe some other organization which I don't want to name, they approach us to implement, provide turnkey solution to make their workshop or their factory smart. So that also we do. So this way we do, and we provide training programs and all, including hands-on training program to young engineer freshers and all. And we are always there for turnkey solution. If somebody has something in mind, he wants to improve his KPIs, so-called productivity, efficiency, or quality, somewhere he wants to that, we provide turnkey solution. So this is all about my presentation. I am open for the questions, I think, right now. Thank you.
Yeah, thank you very much for interesting and very insightful talk, and also demonstrating CMTI capabilities in Industry 4.0 context, sir. If you have any queries for speakers, please you can ask now.
If you need any clarification or anything which you like to know, we are there. We are there to. Yes, please.
Thank you for a wonderful lecture, sir. So we have curiosity on how you predict the remaining useful life.
Very
for
good.
that, statistical averaging methods and all we read, but you have implemented. So I would like to know more about it.
Right. So there are different techniques. Actually, the basic thing is that I think which everybody, a statistical technique you told, maybe based on trending. That is the thing people do based on trending, and if you have experience, you can always do that. So that is a very core technique by which you can find out remaining useful life. Trending. Trending is a technique. So part of statistics only, but you have to see that you should find out how it is degrading. Then other than based on that, only some degradation models are there. How it is degrading. You have to see that how things are degrading, and based on that you can predict. So plenty of techniques are there, and some of them are driven by again AI techniques. So it is always possible. You require some certain amount of data if you want to do such things, right?
Yeah, thank you.
Thank you.
Are there any other questions? If there are no, yeah, madam.
Sir, for mobile robots, you have mentioned that you are using SLAM techniques
yes.
for creating. So, whatever LiDAR you are using, is it like Indian-based result, or you are like outsourcing from like?
No, so that's why our concept, see, very well actually we never say that we know everything. Indians, we know everything, right? So we are actually dual things we are. We are always using some so-called navigation techniques which are available. We are developing, our industry, with our industry partner, we are developing all these techniques.
Okay.
For your, this thing, I don't want to, all the techniques, it is 100% indigenous we are looking, but to start with, you have to start somewhere, no? So we'll use, definitely. I think if you are from CSIR laboratory?
Yeah.
So you know very well. I think we have to take things forward, learn from the best practices, and do it yourself. Thank you. I hope that you got my point. Yeah.
Yeah, if there are no further questions, again I thank speaker, and as a token of our appreciation, we'd like to present a memento. I request Vinit Kumar sir to come onto the dais and do the honor.
Thank you, sir. Thank you, sir. Yeah. Right. So, like to thank NAL for giving us opportunity. We are very much open. We are in Bangalore, and you are all welcome to come to our smart factory. Whoever wants, they can always try to see what we are doing, and we are available 24/7 for your queries or questions. And if you want to make visit, see things, please come. That's all. Thank you so much.
Thank you very much, sir. Now we'll move on to the next interesting talk on Industry 4.0 by Janamjaya Dosh, Tech Specialist Simons. Yes, sir. Thank you. You open it, please.
Firstly, a very warm good afternoon to everyone, and thank you to NAL team for giving us this opportunity to come and present on Industry 4.0. I would also like to thank the speaker before me. He covered Industry 4.0 beautifully, so I will not speak much on Industry 4.0, but I'll speak what it is about for us in the aerospace and defense industries, right? So if I talk about how planes have evolved, like Industry 4.0 has moved from 0, 1, 2, 3, 4, and now we are talking about Industry 5. Similarly, aircrafts have also evolved. We started with the first generation, which was like piston-based aircrafts. They had about 30,000 odd parts in it. Then we moved on to jet engines, F-86, you can see on the screen, 170,000 parts. Then we moved to F-16. These fighters are still in service, roughly 350 parts. So you see the linear progression in parts that is happening, right? And then we did one huge generational jump moving into 5th generation, first fighter F-22, 425,000 parts. And next, we have now moved to 5+ generation aircraft, right? So one of the first one is F-35, brilliant aircraft, right? Any guesses how many parts are there in this aircraft? Sorry? Any guesses? Okay. 6 million parts are there. 600 million parts are there. Both are 5th generation aircrafts. And you see the difference in the number of parts. And this is only because a lot of electronics, softwares, additional sensors have gone into this aircraft. And we are talking now about 6th generation aircraft, right? And this is not just in jet fighters, even in civilian aerospace, when we talk about our civilian land systems, this has been the kind of change that we have seen. And this is what Industry 4.0 means for us in the A&D sector. How do we cater to the complexity that is growing in this industry, right? So traditionally, when we talk about aerospace industries, so it has been very, conservative manufacturing practices, linear way we manufacture. First, someone will design for us, then we will order the outsourced parts or the LRUs, then it will come together, we will assemble using manual processes. So we see these kind of activities which is happening, right? Manual activities starting from, drilling, riveting, painting, LRU assemblies, and you can see the obnoxious positions in which the workers are working on, right? And all this plays into the aircrafts taking forever to build. We are not able to give predictability when it comes to manufacturing, that we will be able to deliver a certain number of aircrafts in a certain period of time. Again, after COVID, we have seen the supply chain disruption happening, especially in the electronic systems, and it has got a connotation with us because, again, a lot of sensors, a lot of electronics goes into it. So how do we take care of it, right? This is what, where we assimilate the concepts of Industry 4.0. There's one concept called as concurrent engineering. So the existing 3D models, existing information which we are generating in the engineering stage, we don't wait for it to complete and then we start our manufacturing practices. We do something what is called as concurrent engineering. As you are designing, we will go and play around with the 3D information, whatever information we have from the product design side, and we will plan our manufacturing activities accordingly. We will see if it is convenient for us to manufacture. If it is not, we will identify the exact places where difficulties might arise, and we will do the changes before. And that way we shift the manufacturing cycle to the left. So one example of this I will show you. So this is Boeing's Immersive Experience Center. Again, let me just play the video and then I'll talk you through this.
Kind of stoop and walk. Go ahead and start walking around.
Boeing calls it the cave.
I believe your design is right here. It's this purple piece, isn't it? Isn't that what you guys are working on?
It's a 3D imaging room.
Look, see if it looks right.
Just one part of Boeing's Immersive Development Center.
What we're trying to do is extend that environment off the desktop into tools and environments where they can experience the product full scale.
Oh, this feels weird.
From 777s to Super Hornets, Boeing can test new parts long before production.
Way before the actual hardware and the chips are cut.
Today, Boeing engineers work with local high school students.
Go ahead and go inside.
The challenge, create a mount for a high-energy weapon in the FA-18 Super Hornet.
And you're seeing your design.
The center lets these students see and test their part on the fighter.
It was a lot bigger and more real than I thought it would be. Like everything was like exactly how it had to be, so I didn't think about that as much. Oh my.
With these Oculus goggles, Rosemary Govan sees this, a full-scale look at the front of a Super Hornet with her team's part colored purple.
This is the size?
You can then understand what it's like to go and grab something.
It's a mind-blowing experience.
Graduate and work at Boeing and then buy one of these.
A great testing solution for Boeing and a tool inspiring the next generation of engineers eager to tackle the challenges of the future.
Be here someday and like just spend all my time working on stuff like that and making that dream come true to other kids like me to actually be in there and feel that same way.
So this is one example of what we saw. They are not waiting for the actual LRUs to be built before they can test its manufacturability. If you noticed in the video, they were talking about integrating a direct energy weapon or a laser weapon into F-18. It is still not in existence, but they have planned the manufacturing for it. Similar ways in aircrafts, when we are talking about how we will do an upgrade to it, how we will change the different seating layouts, for example, when we are talking about building transport aircrafts, right? For different airlines, there will be different seating configurations. So all this changes, all this modifications, we don't have to wait to go to the shop floor and experiment. We can do it by leveraging the information which is already present with us, but by having Industry 4.0 techniques like digital twin or a virtual twin in place and augmented with AR and VR to give you a more better experience about it. So how do we start doing that? We have to follow a continuous and an iterative process. So we do something called as a model-based manufacturing planning or a quality planning, where we leverage the 3D information that is present with us. We give contextual information to it. We do the EBOM, MBOM reconciliation using PLM or any other robust tool which can handle these kind of changeovers and change management. Once our plan is built, we do not take it directly to the physical world. We experiment it using a virtual twin or a digital twin in place. You recreate the exact scenario, either in manufacturing or when the plane is actually in motion, right? And once you have tested all those plans, then you move into actual production. Now in production also we generate a lot of data. You capture all the machine data using IoT devices or edge devices. You bring that data in and analyze on top of that and refine your digital twins. So this will be a continuous cyclical process, and your digital twin will become like a living document for you. It is not a one-time exercise or a checklist item. It is a continuous process which can help us to enhance our manufacturability. So again, this is an example from our tool in Siemens, which we call as Teamcenter. Here we are managing everything starting from your EBOM, which is the product design management also is happening. EBOM is managed. EBOM to MBOM creation can also happen. We can manage the quality plans on top of it. We can create testing routines out of it, right? A lot of test happens, certification happens. That test data can be, test can be planned, managed, and you can have a track of how the change management is occurring. And then, of course, you connect it to the digital twin softwares. You take the same data and validate it using a digital twin. And then, so here you can see they're using that existing data of a wing assembly, and they are doing the assembly planning. Which station will consume which particular LRUs. So here it is the wing in question, which is being checked. Then the winglet separate portion can be checked, right? So these kind of activities you do, and then you move forward to actual manufacturing. Again, one very important thing when we talk about Industry 4.0 is the shop floor to the top floor connect, right? How the IT/OT configuration or the handshake happens. So according to ISA 95, so there are 4 different layers of the technology. The L0 or the L1 layer is the sensors, the physical sensors, the hardware that is there. In L2, we integrate all these different hardware, sensors, PLCs, etc. into the SCADA. In L3, this all information integrates again to the manufacturing execution or MES kind of systems, right? And once you are doing that tracking, tracing, all those activities, you are following the genealogy. You take it to the next layer, which is the L4 layer, where you are integrating with your ERP systems or PLM systems, right? So with us in Siemens, we do everything, starting from the L0, L1, the actual sensors, till the L4 side of things. And once you work in that integrated kind of environment, it's easier for you, because any changes or any data that is being generated on the shop floor gets captured back. And it is even better for the designers, because they are getting the actual feedback from the shop floor, right? And in many cases, when we are leveraging virtual twin, the designs can be enhanced even before we execute it on the physical floor. Similarly, we're talking about testing. For testing also, there are solutions in place where you can, not just manage your testing environment, but also you can schedule your testing environments. You can see the tracking and tracing of all the tests that has happened. And once you do the actual tests, you capture that test data also in fixed templates. So instead of working in Excel or standalone tools, you have an integrated environment where starting from the scheduling till your test data management, everything happens on one particular platform. So you may see that what I'm trying to say is we have to start thinking that how each of the tools that I'm going to procure or use, they talk to each other instead of working on standalone basis. Because if you are working in standalone basis, one hand will not know what the other is doing. You may be doing some terrific work using that one particular tool, but only you can take advantage of it. The entire organization won't be able to take advantage of the work that you are doing, right? So this is one example of how this closed loop system has changed the way business works. This is example from one of our ordnance factory boats, OFB Jabalpur. So they build artillery systems, right? And they had multiple variants that they were building. And the problem that they faced was, we have certain variations according to the geographies. India, as you know, is a very diverse geography, right? We have mountains, high altitude, where they are fighting at, let's say, -30, -40, or even beyond those temperatures. These guns have to work there. Then we have, on the western side, desert, right? They have to fight at 50 degrees, 55 degrees. Scenario completely changes. We have rain forests. So a system, multiple variants are there. Now what happens is, when the change comes for different variants, designers are doing that change, but by the time they send it to the shop floor, to the worker, already the gun has been built to an older specification, older standard, and when the final inspection happens, or sometimes even they find it when it has gone to the field and it has to be brought back from the field, or it doesn't work the way it is supposed to work in the field. And if these systems that we are talking about don't work in the field, you can imagine what will be the issue, right? So they face this problem statement, and along with them, with their management, we worked with a solution where we started taking their existing 3D data for the Dhanush gun system, and we drawn them into that integrated plan that I was talking about. So starting from their manufacturing planning, quality planning, and product design management, all was happening on one common platform for them. Each system could talk to each other. They also dealt with numerous suppliers. So they have a system wherein they can expose certain sanitized data to their suppliers also. So supplier information, supplier testing parameters also flows back into this particular system, right? And only on the sanitized data. So the cybersecurity part is also taken care of for them. And once this data was coming in, then they moved into the shop floor, and they had pre-validated the digital using the digital twin of the system. So in the shop floor, they have a manufacturing execution system in place, which does the permissives or tracking and tracing of how certain systems are built, right? It ensures that the right process is followed and the most updated version is there on the shop floor. They are doing 3D work instructions. So the same 3D data, instead of giving work instructions based on a paper or screenshot, you can give 3D work instructions to the workers. They can utilize that same data to understand exactly how a system should work, or how a machine should be operated, how a tool should be operated, how to put together that sub-assembly, right? And once they are able to do this, they have a complete closed loop system in place, and their productivity and quality has gone up. And this is just one example from one of our defense PSUs, but we have got many such cases, starting from SpaceX, Boeing, Lockheed Martin, US Air Force, US Navy. The speaker in the first half, they were talking about MRO systems, right? So how are we planning to do that? Because these aircrafts or land systems work for 30-40 years. So people will retire by the time, this aircrafts retire. So we have to think from that angle as well, right? So again, it was great speaking to all of you, and any queries if you have, I'm happy to take questions.
Yeah, thank you very much, Mr. Das, for your exciting talk on Industry 4.0 and also suggesting us various solutions. If there are any queries for the speaker, please feel free to ask. So if there are no queries, again I thank Mr. Das for his exciting talk. As a token of our appreciation, we would like to present a memento. I request Ravi Shankar sir to do the honor. Biodata. So we comes to end of this Industry 4.0 session. So we'll move on to the next exciting session, which is on digital twin for aircraft design. Of course, it's a interesting technology which allows aircraft engineers to visualize and simulate aircraft designs before going to prototypes. In this session, we have 4 talks, and eminent speakers will deliver that. And we have a small change in this sequence. Dr. Pratik Deshpande needs to catch a flight, so he requested that he will deliver first. So now I request Pratik to deliver his talk. Then we will follow the same sequence. Pratik, 4. Okay. So Pratik and Manoj will be talking, and Manoj will be the lead speaker. Yeah, please go ahead.
Thank you. Color mic, you can put it for them. Because I will speak at the end also a little bit. Good afternoon all, and we would like to thank NAL for giving us an opportunity today to speak on digital twin and what we are doing at Altair and how we are helping our customers as well as other DRDO labs from a digital twin perspective. So just a quick brief on what Altair is. Altair has been in the market for the last 40 years. It was founded in 1985 and we are headquartered in Detroit, Michigan with over 81 offices across the globe. And these are some of the customers that we are working around the globe, as you can see, including government, defense, heavy equipment, aerospace, automotive, though automotive being our USB customers. Now, in the recent years, we have seen a lot of paradigm shift. And what do I mean by paradigm shift is, the first paradigm initially when it started was experimental. So wherein, we had empirical describing natural phenomena. We tried to make some prototypes and try to understand the behavior. Then the second paradigm is theoretical, wherein we started, creating models, mathematical models, and try to understand the behavior. And finally, a couple of decades ago is where the third paradigm came into picture, which is computational. We started with static analysis, finite element analysis. We ventured more into building finite element analysis and try to virtually represent how a model would behave under certain conditions. And finally, in the recent years, now we have seen a fourth paradigm, and that is nothing but which is more data intensive. So which comprises of data exploration, design of experiments, data analytics, and digital twinning also. Now, we today will be covering majorly on 2 topics. One is the digital twin, which my colleague, Mr. Manoj, who is the subject matter expert for digital twin and who has been working with multiple different labs on developing some of, very genuine digital twins. And at the end of the session, we'll also talk a little bit on how AI and machine learning can be combined not only with digital twins, but with respect to physical simulations as well, which can be included in digital twin for a faster and effective product development. So over to Manoj now.
Thank you. I hope you can hear me. So I think Pratik briefly touched upon what are these different paradigm shifts that we are seeing. And at this stage where data comes into picture, we really see a lot of value in digital twins because digital twin, and I think many of us from morning today, we are sort of talking in some fashion about how these digital twins are going to help industries. And for us, maybe I'll start off giving an introduction about what really digital twins mean for us and at Altair, and how have we been working on digital twins extensively with various aerospace and defense organizations. But to start with, digital twin is a personalized, evolving, dynamic, real-time replica of any physical asset. An asset that could be a product, could be a process, could be an equipment as well. But we really see value of digital twins in two forms: the physics plus data, purely grounded in physics, but collecting data from the sensors and combining these two technologies together. When we really talk about digital twins, I think everyone has their own definitions, and it's sort of a buzzword which is quite a lot used. But we see a lot of stages at digital twins. To start with, I'll start from that extreme corner on one side, which is purely manual, which is hardware prototyping, where there is a bit of a manual sense. There are no sensors as such, but it's just completely a manual sort of a plant model that you build in. The first step, what we really term it as pre-digital twins, is where you start doing some simulations-based prediction. I think most of you here have been already working on physics-based simulations and applying them to these hardwares. The next step is to connect these assets with the sensors, and that's where we start looking at real-time visualization, sort of monitoring. And I think some of the speakers covered about this as well, where VR, AR comes in, and some sort of a manufacturing analytics as well comes in. The next step is where AI gets added to really start predicting things and improve things. And that's where we see sort of real-time predictions for the assets, where we start looking at, say, remaining useful life, degradation effects, and so on and so forth. Essentially do a predictive maintenance at the end of the day. And finally, a closed loop true digital twin is what is the end goal, where we see a living and a breathing model, both from a physics plus AI standpoint, which not only does a conditional monitoring of your system, but also predicts and makes sure that before a particular event occurs, it should give you an alert that this is the sort of extent of life that is left to that asset, and we need to prevent it. So having said that, let me just give a quick view of where we operate on from a digital twin standpoint. We have all the three stages. I'll start from the right side, because a lot of digital twin today is more on the operational side, where there is an asset already running. Okay, and that's where we look at remaining useful life from in-stream real-time streams of data. But we also can look at a production level, testing level, or a manufacturing level digital twins, where we sort of detect early test failures, monitor real-time manufacturing KPIs, and do these VR AR studies. And a step before that, when there is no sort of a physical prototype, but you want to bring AI to improve your design processes, to augment your simulations today, is what we really term it as a design digital twin, where modern tools like AI and ML, along with the mechatronic product development, really help to improve the design process today. So with that, let me give a general workflow of what Altair does in terms of the digital twin. I'll start with, it's just a very representative workflow or a deployment workflow that we see. For instance, you have a physical asset and you have a real-time operational data as part of sensors coming from that physical asset. This data can go to a physics-based twin, which is essentially a living model of your systems, purely grounded in physics. The physics can be a 3D model, could be a reduced order model, or could be just an equation-based 1D model, but essentially a living model. And this physics-based twin will help us to do multidisciplinary integration, dynamic what-if scenarios, let's say prescriptive analytics, recommendations and actions. So for example, for my asset to be running smoothly, based on my environmental conditions, what could be the best design variables that I need to play with in order to make sure that the situation doesn't go from good to bad. And that's typically a physics-based twin, but we also have an AI-based twin. Altair as a platform, with its RapidMiner platform, has an enterprise-level scalable AI technology today, through which we can build AI models which can be deployed, and for which we have this intelligent twin to do prescriptive, predictive analytics, predict remaining useful life, and do a predictive maintenance. So what do we see value in digital twins is really a combination of these two, a physics-based plus data-based twin. Because for engineering problems, just AI may not solve all the things, but we really need a sort of a convergence between physics and AI. And that's what Altair offers to the table, where you have all the solutions from a simulation standpoint plus the AI/ML standpoint in a single sort of a system of licensing. So broadly, these are the different stacks of products. I'll not go into the details, but I'll just quickly talk about what these mean. So HyperWorks as a platform is a completely simulation stack, where we talk about physics-based simulations, system simulations, optimization, and AI-powered reduced order models. We have an end-to-end data pipeline using a RapidMiner suite, which is starting from data preparation to model building to deployment of your models on cloud, and real-time streaming and visualization, which is a very powerful engine for deployment of digital twins. And finally, IoT stack, where we have products for getting the data in real time and passing it to different type of models. But where does digital twin really stand here? It's sort of a convergence or a sort of a flexible convergence of all these three different stacks. And we see a lot of value when we put this digital twin vertically, because now based on the application and the usage, customer has a choice to flexibly choose the IoT plus physics or a data and the real-time streams, etc., to really build and streamline an application of digital twin. That's where our digital twins are a vertical stack, where we can take our subsets from each of these different stacks today. With that, I'll probably jump into some of the applications. We have been working especially on aerospace and defense. A lot of applications, we've been working extensively on digital twins, reduced order modeling, physics-based simulation predictions, and so on. But to start with, I'll probably take just two of these examples to sort of give you a picture of how and where we've been applying this digital twin. These are solutions that have been deployed at the customer place today. For instance, Leonardo, there has been a very active engagement between Altair and Leonardo to develop these accurate mechatronic digital twins to not just optimize their control systems, but also reduce their physical prototypes to start with. So I'll just talk about this particular solution of airborne radar digital twins, wherein their entire problem was during the in-flight, their radar had a lot of transmission losses because there were vibrations. And the idea and the challenge here was to really develop a model that could correct their radar transmission losses based on the in-flight vibration that they had seen. And engineers there needed to predict that behavior and the effect of vibration and other structural systems behavior on their radars today. So it's really a holistic sort of system simulations or a digital twin that need to be done. So to start with, we combined all the different physics for this, starting from dynamic motion to high frequency electromagnetics to control systems to complete acquisition of the signals, and developed a model which could essentially represent the true behavior of radar systems based on all the different physics that are acting on it. How did it help us? It really helped us and them in order to sort of understand how every subsystem or every physics is really affecting the in-flight transmission losses, and then sort of optimize the performance at the overall product level. And what you see at the end of the day is a reduced order model, a dynamic nonlinear reduced order model that we had built that could estimate the side lobe levels, the main lobe levels of the radar based on the input characteristics that we had coming in. So I'm not going into the details of this, but just to sort of summarize from what they mentioned, it is really important that digital twin condenses physics plus the learning models, the machine learning models, in a single environment so that we can build a process to effectively do a predictive maintenance. Post that digital twin project, we also extended that to multiple other activities at Leonardo. For instance, for example, here is an interesting case of multi-objective optimization of power units and how they used it for airworthiness certification. I personally like this very much because this was a typical aeroelastic coupling process, and I'm sure many of you here are probably working on these sort of co-simulations between aerodynamics and structures. I think Leonardo as well had a very similar challenge where these 3D models are expensive to simulate, and what they built was a co-simulation ROM, which is a pure play structures plus aerodynamic ROM that could really help to do a seamless co-simulation between the two, to do a quick design iterations, design studies, and so on. There are a lot more details out there in this link, which you can definitely go through in order to understand how the structure plus CFD ROM was, coupled here and built. The second example is on Rolls-Royce. Again, this was purely, while Leonardo was more of a physics-based sort of a twin, this one was more towards, AI-based sort of development. So the collaboration with Rolls-Royce really helped them to apply data science to their huge amount of testing data that they already had. So the potential is enormous because they could reduce a lot of sensors already, and this work is still ongoing in order to extend that activity. But to summarize, it was purely a virtual sensor development, wherein they have this complete model or systems of their engine, and AI and ML model were used on their jet engines based on the historical sort of test data, so that we sort of develop certain models which could predict these anomalies over the system. So this anomalies here were using the historical sensor data from testing. Some, of course, the feature engineering and the deep learning comes into picture. And the main driver there, as you see, is to determine some of the features which categorize or which are important for the poor performance of the engine as well. So that information also we could start sort of understanding from the system as well. So a very similar exercise was also done for an engine manufacturer locally in India as well, where a virtual sensors was developed based on the huge amount of test data that they had today for their turbine engines. So to sort of summarize, I mean, even this use case is where, this is another use case though, but yeah, here it was more of, identifying the right sensor placements. Okay, so one of the challenges is there are n number of locations. How do we sort of get the right strain locations? So we used our RapidMiner platform, which is meant for all the AI and ML model building, to cluster the entire data sets that we had, and then choose and identify the best strain gauge locations. And ROM AI, which is our reduced order modeling application, is then used to predict the loads based on the best strain gauge locations that we had. So it's a nice workflow to smartly use AI to get to reduce the number of sensors and smartly choose those best locations for us to estimate the loads more accurately. I think this video is probably not running. This is a very basic, simple video of a deployed sort of a predictive maintenance on a bearing. But I'm just here showing this because this is a web-based dashboarding where you can dashboard all of your real-time streaming data coming from databases, coming from sensors, or coming from machine learning models. So everything that we spoke till now, physics or data, will all go behind this. And what you see is this nice customized UI that can be dashboarded at your premises, so that you can visualize everything that's happening in real time, be it from test, be it from actual assets running remotely. This is just for the bearing, but yeah, essentially you can see all of those data. So here we can do starting from descriptive analytics to describe your sensors, then go for the predictive analytics where you start predicting based on the ML models that are deployed, and then you can also do a prescriptive, which will also give you what ifs or recommendations or action where simulation models can be run in behind. So it's a complete closed loop, end-to-end, digital twins that we can look at today. So yeah, that's a quick brief. But to just summarize, from a digital twin standpoint, there are various building blocks to digital twins. There are a few from physics, for instance, CA simulations that we all know about. Then there is reduced order modeling, where you can create statics or dynamics or a nonlinear or linear ROMs, to machine learning, data analytics, IoTs, and so on. So these are really the building blocks to flexibly sort of build digital twins, and our offerings are more or less complete in terms of building these flexible sort of a digital twin. So that's all I had. Thank you, and if you have any questions, please feel free to ask us.
Thank you, Pratik and Manoj, for enriching us with various concepts of digital twins and solutions which Altair offers for aircraft design. So if you have any queries for speakers, or will, yeah.
Hello. This technology in prototype manufacturing and flight testing activities, can it be applicable?
For flight testing activities, yes, definitely. It can be applied.
Can you just throw some light on that?
So for flight testing, so you'll have some physical assets still, or is it a virtual testing that you're looking at right now? When I say virtual, is it more like a sort of a model-in loop sort of testing, or?
No, when it comes to airworthiness certification, there are certain things you have to have that flight testing activities.
Correct.
So like whether it is in America or Europe, rather than testing through that, is there any compliance related things can we able to do?
Yes, there are. Okay, probably we've not covered that here, but there are some compliance requirements. I think you're talking about some of the standard requirements as such, right?
Yes.
So they are part of the platform today. So we can use them. So these are some ISO standards or MISRA standard compliance and so on, which can be used for deploying your flight control systems.
Okay, thank you.
Yeah, if there are no questions, we would like to thank both the speakers, and as a token of our appreciation, we would like to honor you with a small memento. So I request Dr. Aruna, Head DTS, to honor the speakers. Please. You can just move. So now I call upon Ms. Swati Hiremat for her talk on digital twin. She is from Siemens. बड़ा कर दो बाद में PPT ओपन करना छोड़ दे वो PPT ओपन कर
Good afternoon, everyone. Modern aircrafts, as we saw, my colleague Janmejay did talk about how the number of products or the number of components in the modern aircrafts have changed. And most of these components that have really gotten added into these newer generation aircrafts are mostly electronics or electrical. What this really means is modern aircrafts require more power. What it means is there are more electrical systems than there were ever before. And to make problems even worse, what it really means is this is adding to a higher complexity, higher compliance risk because of complexity, as well as the frequency of changes that are going to come in because of mission demands. What can help is an electrical digital twin, a digital twin different to all of the simulation digital twins that we will see today. So let me tell you a story. Let me introduce you to a drone called Angel Owl. This drone has been commissioned to fly over forest fires and take high resolution images and share the data real time with the ground personnel. The idea here is that the ground personnel can take a look at these images, quickly identify in which direction the forest fire is spreading, and try and find out, how they can fix and help doing that. Now, what needs to be done for this is, Angel Owl is a tactical drone, and she needs to be retrofitted with a new LiDAR system to match this mission's need. It's a good thing that the Angel Owl was designed on the Siemens Xcelerator portfolio, which means we can go in and make these changes quickly and validate these changes quickly because I already have the digital twin available. Now, through something called as an integrated digital thread for electrical design, what we are going to look at is how are these changes impacting the entire system. Now, from that analysis, I will also start making the actual implementation on the physical system. From that, I will get on to engineering the wire harnesses, making these wire harnesses ready for manufacturing. And then at the end of the day, I will also make sure that all of these changes propagate to my maintenance manuals so that I can also keep maintaining this Angel Owl for all further missions. So let's start with the first step, which is to bring in the change, to analyze the impact of the change on the systems, and then derive the rest of the electrical proposal. So to start with, I'll have the system model updated in a system modeling tool. Without having to redraw anything, I can import the changes made to the functional model. Since we are working on the data that's already been created, the system will already show me visually what are the new changes that are coming in. I can then incorporate the changes into the platform of the aircraft, allocate the functions and the signals through a rule-based logic, and from this I'm also able to make design iterative changes and see its impact on the real-time metrics of the data. Now that I am convinced that this is a good architecture to go ahead with, I can ask the software to generate the logical schematics. Now that the logical schematics have been created, my next step is to implement it on a physical system and make sure that these changes are propagated towards the final wire harnesses that get into the aircraft. Now, what I'll start with is that I don't have to start with redline documents or PDFs or paper. What I'm starting off with is the changes that have come in. The system already tells me what are the changes that needs to be done through a cross-project highlight. A to-do list will also guide me through to how to make these changes into the system, what are the things that needs to be updated. And once I start placing these changes with the tight integration that exists between an electrical system and a mechanical system like NX, I'm also able to update the connectivity and ensure that my mechanical systems and my electrical systems are in sync with each other. While I was working on the electrical design, the mechanical engineer was also working on the mechanical design, and now they are both in sync. Now I'll bring back the mechanical design into a 2D platform and ask the software to tell me what is the best possible way of routing these wires inside the aircraft. And through this best possible route, I will also identify any need of a running brake that is required. Now once a running brake has been identified, now that data will propagate back into the wiring diagrams, updating them for further design. Now comes the next activity. I've finished my physical implementation, but all of us know that's not what's going into the aircraft. What really goes into the aircraft is a wire harness. Now my next step is to engineer the wire harness, make sure that everything is ready for manufacturability. I have the manufacturing BOMs created. I also have the loom boards or the form boards generated for the shop floor, and then go further down. So what I'll do is I will open up Teamcenter where I have the latest NX 3D routed data available. I will import that into my platform. I will quickly flatten it out into a 2D variant. I will, make some changes on the alignment and, how I want it to be placed on the drawing. You will see a lot of automation in terms of, the symbols being selected, the lengths coming in from 3D and all of that. The next thing that I'll do is I will also use the automations built into the software to engineer the wire harness, where I can get the software to do some calculations on the bundle thickness, the bundle lengths, the wire cut lengths, the weight of the wire harness, and also some automatic part selections like the tube part numbers, the terminals, the plugs and the seals that go into the connector, and ensure that the data or the design is right the first time. And once I have this design updated, I will go ahead and start creating my 1:1 loom board drawing. And in this loom board drawing, I have to make sure that these drawings fit into the real estate boards that I have available, but making sure that none of the criteria like the minimum bend radius are violated. I do this, I ask the software again to run some automation to select all of the jigs for the connectors as well as the entire bundle, and have that updated so that these drawings can be printed out on a plotter, sent out to the shop floor, and have that pasted on the board for the manufacturing assembly to start. Now once this is done, I can send this back to Team Center where it is stored in the repository and available for the manufacturing teams. Now we've at this point in time, we've incorporated the new system, we have implemented it physically, we have created the wire harnesses. Now that's been sent to the manufacturing, and the wire harnesses are now getting manufactured. What next? What next is to make sure that this data now is also incorporated into my maintenance manuals, so that for all further missions of Angel Owl and any further changes, I can also maintain this aircraft on the field. So the first thing is to use the existing engineering data and also bring in all of the new data that we've just added. With a functionality called fetch related, I can bring in all of the new changes and go ahead and convert an engineering drawing to look like something that would be useful for the service technicians. With a few clicks of a button, I am able to generate diagrams that are more appealing and more relevant to a service technician. An activity that would have possibly taken many days is now reduced to a few minutes, and the new data is available for the service technicians. The next thing that we do is ensure that we also bring in a 3D view into the maintenance manuals, so that I can actually look at the location of a component that's not working. I can then look at its related drawing or the wiring connectivity, or ask the software to generate a wiring diagram on the fly for just this particular component. For this component, I can then find where is it present in the aircraft, how do I access it, and how do I make these changes. I can look at the face view of the connector, all of the details about which pin, what are the measurement that needs to be made, what should be the reference values that the technician should be looking at, is all present in one single sheet. Once the technician does all of the measurements and realizes that the part is faulty and it needs to be replaced, a shopping cart is available right on the same screen, where the order for the replacement part can be placed, and everything is done in one screen without the technician has to go and refer a 1,000-page document, go through multiple links that says go to page number 20, go to page number 300, go to page number 400. So we remove all of that ambiguity and bring everything into one screen, and the fault is identified, the fault is checked, the replacement part is ordered, and the activity about fault diagnosis and maintenance is done. So what we did really here is we've transformed a tactical drone into an aerial fighter through something called as an electrical design across the integrated digital thread. This was possible because Capital as a solution delivers dramatic productivity improvements now by enabling a digital transformation of the EE digital thread, so that we can deliver capable platforms that fulfill customer missions today, tomorrow, and always. Thank you. Any questions? Happy to help.
Yeah, thank you, Swati, for enlightening us with your platform, which will really enhance the productivity. If there are any questions for the speaker. So, if there are no questions, once again I thank, and as a token of our appreciation, I request Dr. Pankaj, Head System Engineering Division, to present a memento. Steady, steady. Now we'll move on to the next talk. Next talk will be from Mr. Javed Herial, a consultant director from CSC India. Over to Javed.
I'll try to complete it. Thank you. So, good afternoon, everyone. It's a great privilege for me to address this August gathering on virtual twin for next generation air vehicle systems. So, what I would like to spend some time is what is the revolution that is happening in the air transportation that is going to change the way we travel within metropolitan areas. As we are citizens of Bangalore, we always realize that we spend most of the time on the roads, and we know that it is how difficult it is with the growing projects, with the growing responsibilities. How do we reduce the time on the commutation? That is where the entire world today is looking on the revolution of changing the transportation. So basically what we are trying to address here is we are talking about advanced air mobility, how advanced air mobility is going to way we travel within the metropolitan cities. Here I would be taking an example of electrical vertical takeoff and landing as an example and tell you how virtual twin can be created using 3D experience platform of Dassault Systems and how it helps our customers to validate their products is what we are going to talk about. So quickly, if you really look at it, advanced air mobility is a new way of transportation. And if you really look at it, advanced air mobility is in genesis. We are witnessing industry shakers that disturb the aviation industry with their innovation of new novel electrical architectures. Now, with this new way of architecture, what is its goal? Its goal is to transmit people from one location to the another location by reducing the carbonization, which is destroying the environment of the world. That means we are talking about sustainable products going to be developed, designed, manufactured to protect the interests of our future generation. So there is a large leap that is going to happen. Now, many people talk about what is digital twin, what is virtual twin. I believe we as Dassault Systems 3D Experience Platform Technology, we believe that virtual twin will help us to validate the behavior of any product. Now, what exactly is the definition of the virtual twin? Virtual twin is a true representation of the physical object. The physical object could be a eVTOL in our case, which is used to transmit, but having alone a eVTOL will not be able to help us. It also requires, we call it as vertiports, like helipods. We need vertiports to transport, and we need infrastructure to do that. Third thing is, it also requires airline operators who operate it, is the three elements that is required. If you really look at why we need to look at this particular segment, you can see here, The expectation is $115 billion. Okay, and it is also closely associated to the passenger segment. That is the reason why we are discussing about this. So if you really look at it, developing a virtual twin in a complex regulatory environment, meeting the manufacturing rate at which the number of eVTOLs is required, the infrastructure required is a quite challenging task that we need to do. For a moment, let us look at the time and see what are the challenges that we as an industry will face in order to address this particular segment. If you really look at it, we have the first enabler is the climate change. If you really look at it, aviation industry contributes 2.5% of global carbonization as of today, which may go to 40% if nothing is done in this. That is the reason all the R&D organizations across the world are focusing on the new technologies, and we have already witnessed the electrical vehicle segment picking up in India and across the world. What is its contribution on that? So similarly, the same kind of changes are going to be there, which we need to address it using the battery technology. Of course, it is not just about battery. What I'm going to try is all the R&D organizations are working for special alternate fuels. They are looking at hydrogen as an alternate fuel, and they're trying to continuously evolving the product. So as a designer, we need to explore all this technology, and we need a platform that can help us to do that. Similarly, the second important aspect is regulations. If I look at eVTOL itself as an example, if we take the eVTOL and then see that if eVTOL is to be designed, it has to be designed contributing to the international market, and it has to satisfy the compliance requirements. And if you really look at it as I'm speaking, yesterday FAA has very clearly announced a new standard for cyber security laws for an aircraft industry, which is applicable for passengers of more than 19 seats. You can Google it off, you can be able to get this information today. And the weight of around 19,000 tons. Now, the way the industry is looking at it is we are going at a very rapid rate of having the technology, having the standards getting changed, integration, and so on. One big challenge is in the absence of international regulatory rules and local industry upgraded to that could be a challenge in developing this industry. But there is a need for all of the industry stakeholders to come together and work upon this potential, which is having a very big potential in the future. Third thing is on the technology. If I really look at the technology, as most of the eminent speakers throughout the day has told, that battery is a very, very important aspect. And we believe battery is very important for air taxi because it is designed to take a short duration where it transports people from an office to the airport or from airport to an office. But one of the challenges with respect to the battery is how do we increase its energy storage? That is also very, very important aspect that we need to think upon. And we also need tools which talks about what happen if I have a battery cell pack. What if I have a different kind of material for battery? It could be sodium, lithium, and so on. How do I evaluate the performance of my material on my product? This is a generation where we are going through upon a lot of transformation. The innovation itself can come from material. And we also talked about material not availability. That is a different challenge. What I'm talking to be as an R&D organization, if we wanted to think about innovation, we need to have the technology that can help us to evaluate before a physical product is produced. That is where the virtual twins will play an important. Fourth pillar, which is very important, is on infrastructure. We need to have, if this has to be successful, then the infrastructure, the cities we operate need to have vertiports at various locations. And we need to have eVTOLs which caters to the 4-passenger, 6-passenger. It could also be for transport, it could also be for cargo, it could also be for emergency. So there is a lot of potential today, like what we order from goods from a store, where somebody will bring it and give it to us. Today we are targeting the future air mobility in this nature. That is where there is a need for 3 pillars, okay? And we believe that virtual twin experiences, what we call a 3D universe, which can integrate all the 3 communities. I'm going to talk about these 3 communities here. Aircraft, basically the OEMs, the infrastructure or vertiports, and airline operators. They 3 needs to be together. And when I talk about a virtual twin, I should be able to design virtually a eVTOL and see that behavior with respect to vertiports. I also should be able to validate the demand on that particular day and utilization of my vehicles to do that. So there is an entire universe. There is a behavior of the aerodynamics that hovers over the city that I need to take care. So virtual twins is one which helps us to validate the behavior of the systems. So what I do is, in the interest of the time, I'll just quickly, okay, sorry. Oops. How do I play this video? Yeah, it's not happening. Yeah, here. Okay. So for the next 10 minutes, what I would like to take is, when we talk about virtual twin, basically what we need to do is, there are various segments of the product development. The first thing is the program. Here we are helping with one of our customers. This is an actual case what we have done with one of the eVTOL companies, where they are preparing their project schedule on how they would like to roll out their eVTOL, where they are planning the entire work breakdown structure, and then trying to plan and manage and monitor the execution of that. So I'll not go in this because many of us know, but I would like to tell you very clear experiences. Every organization has different source of information. Maybe they may have a PLM system where they manage the CAD, but if they go to the commercials, they have a different platforms where they track their purchase orders, when is that equipment arriving at. Unless you take all these information sources, you will not be able to monitor and control the project. So that is where what we need to do is, you need to see that how you will be able to manage this. And then what we also need to do is, I would like to tell you how Dassault Systems help this organization. We put a project plan, we involved all the stakeholders, we integrated with the various sources where the information is there, and then we use the state-of-the-art SysML technology which is embedded in 3D Experience platform to model a high-level mission objectives, the performers, and then the scenarios of the subsystem that address this need. So we have a basic system architecture tool which helps us to validate it. Now, once we create a mission objective, then what we do is, we create a unified architecture model using UAF standard. Our system model tool will help us to create a UAF model. And then there, we take the high level KPIs that has been there. And what we also do is, whenever we define each system, what we do is, we define what are the parameters that are very interest for each domain guys, and then we reiterate in the loop to identify what are the key parameters that influence my whole mission objective. So every time any domain guy, they try to validate their specifications, they always need to keep into mind that the overall objectives that need to be achieved. The next level is how you take it up, the various concepts. Now, once you define the high-level KPIs, what you also do is, you take this high-level KPIs to the next technical subsystem level, and then what you do is you have a cyber grip methodology which helps us to have a connection between aircraft level, system level, subsystem level to the component level, okay, wherein we take in an operational view and connect the operational view to functional, logical, and a physical view. So if you are not able to connect these elements together, we may not be able to achieve the virtual twin. The reason is we need to know the traceability, we need to know the impact, we need to understand what could be the impact of output on one of the element, because in the entire iterative process we'll be changing so many specifications of the parts to optimize my behavior. Not only this, what we also do is we also try to do a lot of configurations. You can see here I'm trying to develop various configurations. I keep my mission as it is. I define my objectives, I define my goals. Maybe my objectives here is to reduce the carbonization and to reduce the travel time. When I do this, what I also wanted to do is, I also wanted to create a various configurations by varying the various design parameters which are very critical to achieve my mission. This is only possible by using a simulation technology where we can create a multiple configurations and then we plan the global FEM model to integrate this with respect to the analysis and compare the results of this model. Now to do this, many people say we do it. What is really required in the background is you need to have a parametric model with which you will be able to create. In this use case, we are trying to take the wing where we are creating the ribs and spars at various locations to arrive at the various configurations. What could be the impact? Because here when I am using a battery, weight is very critical and I need to have the performance and I need to achieve my mission within the battery specification. The more I achieve, I will be more beneficial and competitive in the market. So to do this, we have a lot of tools which in there, which helps us to optimize the design. You can see this is not the, this is actually use case what we have done with one of the startups, how we will be able to engage and do the parametric study. Then once we get a different configurations, we loop these models, whatever the iterative models what we are, with the FEM models, and then we simulate it and predict which is the best configuration. In this eVTOL case, one of the important regulation was the noise to be identified, because these are going to operate in the city environment at various operating conditions and we need to do an analysis of that. So it is very important for us to do the noise analysis and of course all the aerodynamic load analysis, okay, structural analysis, impact analysis, static analysis, bird analysis, EMI, EMC analysis where you want to put your sensors, where you wanted to optimize the location of your battery which has an impact of center of gravity, and then how do we control the weight and CG of that. Anyhow, these are all part of that which many of us are worried, right? I'm trying to specifically focus on key areas which is related to the challenges of eVTOL. Once we do this, we can also do a lot of comparison study between each of the configuration and see that which is the best configuration to meet my mission requirements. Again, I will say, in the same time, we need to see that we are able to achieve for cargo separately, emergency separately, as well as taxi separately. So you can see how this all will be done, and then you will be able to see how I will be able to look at the various key parameters. It could be endurance, it could be performance, it could be range, and so on. Here you can see that there are various cabin configurations that we can achieve with respect to our model. And second important aspect is how these eVTOLs can operate, behave in a vertiports is also very important. We also need to know how the vertiports has to be designed. What is the area? What are the precautions that needs to be taken? Then only we will be able to do. So that is the reason why we also do the aerodynamic simulation. We also do with respect to the vertiports how this behave. And similarly, here you can see on some of the parameters like tilt motors, the number of engines, also is a very important parameter in order to achieve. We have a virtual tools with the help of which we can validate the behavior of that. Not to, just to restrict on this, what we also can do is we can also simulate the behavior taking into the account the environmental parameters and operating conditions and see how this will behave, how my battery performance will vary at a various operating conditions. That is very important. So in this concept, in the interest of the time, we are coming out with a strategy of V plus R, which we call it as a virtual and real strategy. And in the aerospace industry, even though we do virtual test, we cannot escape from physical test. So what we have is, we have a virtual pyramid where virtual tests and physical tests correlate, and we can give the feedback from physical test to the virtual test, improve the fidelity of your simulations. And we also talk about, I don't want to spend much time, this particular eVTOL which we are talking about is also talking about composite design. It is talking about electrical wire harness. We know all these challenges because we know what is ECAD tool, wiring diagrams, theoretical diagrams, then it goes into the routing diagrams, then on the form board diagrams, what is the relationship or integration between those things. And in addition to that, since this is a new technology which we are doing it, so what we also do is, how are the various manufacturing technologies can be enabled is also enabled here. Here in this example, what we are showing is additive manufacturing. So just quickly, in the interest of the time, what I just want to convey is, similarly we can do for vertiports. Since my time is away, so what I wanted to talk about is the last thing. When you want to operate a air mobility system as a service, what is very important is you need to get requests from the passengers. Without passengers, this industry will not work. How would they do it? And then once your request is coming, you need to optimize the fleet. What location to what? How do we manage that? This is where is a virtual twin can play a very, very important role to manage the customer demand, reducing the operation cost, increasing the flight revenue. And this is the model which we wanted to do. In addition to that, what we also have is, we have connected this with this solution, by the way, is deployed onto the cloud solution. And what we also have given is, we have given a marketplace. For example, for rotors and all, for the particular specification, from the 3D Experience platform, they can raise a request for the availability of the components in the market across the world. And people can do it. This is not available on premise, but this capability is there on cloud. So this is where we have connecting the dots to secure the value of that, and digital continuity needs to be ensured. This is what we believe. And these are the few references with which we are working across the industry. These are the few people who are coming out with this. And this is what I have to talk about virtual twin. Thank you.
Thank you, Javed, for a fascinating talk and introducing us to virtual twin. Yeah. Thank you very much. If you have any questions, yeah. Can you pass on mic there? Go fast.
Hello. Yeah. It's excellent presentations. I have one query here. As you have taken the system as a complete product from end to end, you have taken mission scenario. What about the communications requirement? Like in this, your thing, can we estimate a path loss calculation? Can we know how if you are flying, particularly some obstruction is coming, can we communicate where there is the navigation requirements? Is there any way to link those?
Yes. This is very valid question. I don't know. I didn't have a time to tell you about it. This is part of the strategy of the virtual twin. See, just to imagine, if you wanted to do that, there is some sensor that is detecting the information, right? That information has to be passed on to this. So at a high level, I'm addressing it to you, but we can meet outside and discuss about it. Yes, this is possible use case. And this is one of the use cases. I take a simple example of ADAS, which is used on the cars today. And we are doing it very exclusive work with Mahindra and Mahindra. Okay, they have decided for the 3D Experience platform, where the car is going, we are talking about autonomous cars. When the car is going on the road, it detects any of this. it has to sense it to send it to the control law. The control law will have to take the decisions based on the parameters. Okay, so there is a technology which is available which can be extended to here. In fact, this technology is first there for aircraft industry, then it moved to the transportation mobility, but we should be able to understand.
Thank you. Yeah, thank you, Javed. As a token of our appreciation, we would like to present a memento. I request Jagdish, head quad, to present a memento to Javed.
Thank you so much. Thank you so much, sir. Thank you so much. Thank you, sir.
Yeah, we move on to the last talk of this session on digital twin by Pranjal from ANSYS Bangalore. Over to Pranjal. You can take a corner.
No, metal. No, not this.
Third one, ANSYS. First one.
Opening up, right? Okay, I guess.
This one? Yeah.
That one? No, this should open. This is open. It's working, it's open. Okay.
Already open. So close.
It should open. Shall I start? Sure. Am I audible at the back as well? Yeah, okay. So today I'll be talking about majority of many industry speakers have talked about the value of digital twin and how it allows you to pre-validate your designs before building up a physical prototype or going into the manufacturing side. And even the industry speakers have talked about how the value is there for the digital thread and how you arrive at digital twin, how you build up the digital twin for your system. So this is where I'll be talking about ANSYS, what ANSYS offers and how we have enabled customers to perform requirements verification and design validation through the use of model-based system engineering approach and digital twins in our virtual product development ecosystem. So ANSYS has a lot of offering, but you might already know ANSYS in the field of simulation. What ANSYS has shifted in the past couple of years is into the side of digital engineering, where you have model-based system engineering requirements and architecture, build up connections, digital thread, safety security requirement studies and digital twins, as well as your AI ML integrations and building up of hybrid models. So there are various aspects where ANSYS supports. So on the digital engineering capabilities or supporting the digital transformation within an organization, as we are all aware, any product, any project starts with a stakeholder requirement, and based on stakeholder requirements, you develop your system level requirements. Based on your system requirements, you have a high level system architecture, what you have to build up, what will be the requirements for it, what will be the parts that will go into those systems. And then you venture into the detailed design part, where you build up the physical design, that is the 3D models, and the software design, where you have embedded codes generated for your software systems. And then comes the important part, where you integrate all these high fidelity simulations, condensing them to a reduced order model that was talked about, and integrate them to a system level model. And when you utilize this system level model, that is a virtual prototype having your simulation physics embedded, or if you have a data and integrating your data, real-time data, or the product field data into these models and creating fusion models using AI/ML techniques, then you can build up a digital twin, a prototype that you can actually, virtual prototype that you can utilize for your requirements verification and design validation studies. So there are several products that are there in our ecosystem, but I'll be talking about the product chain that allows you to arrive at build up of this digital twin models. So this is a virtual product development cycle. We are all familiar. At the top, we start with the requirements definition, where we have various requirements coming from the stakeholder. Then you have design reference missions. You can build up those design reference missions. As someone in the audience talked about the path loss calculation at the high level, that's where we have a tool called as Ansys SDK that allows you to build up these design reference missions, do the high level ConOps, and you to do the high level simulation on path loss calculations and various such specs. Then once you have requirements built up, then you have system architecture modeling. In a couple of previous presentations, you might have seen the system architecture models like Rhapsody, Cameo, and there are multiple tools in the market that allows you to decompose these requirements and then also decompose your system architecture. And the important part that was also talked about in the previous sessions was allowing the design exploration studies, allowing that trades, allowing to make that decisions at the early stage by verifying your requirements at the early stage, utilizing either 0D, 1D equations or some past 0D, 1D models that you have, or some 3D models that you have utilized in the past, and validating your requirements at the early stage and qualifying the design cases. So that's why you need a connectivity from these system architecture model, the digital thread that pass on the data from the system architecture model to the analytical workflow where you perform these trade studies. That's where a tool called as Ansys Model Center comes in. You have then, once you have a high-level system architecture, you have defined your system, how you have to go ahead with. You can perform safety studies where you can perform HAZOP, HARA, those kind of FMEDA, those kind of thing in a single model-based environment. And then you have software design applications where you can define your logical architectures and you can generate certified embedded codes. As someone talked about the certification for control systems, so we have AnsysCade that allows you to generate certified codes directly from your logical architectures, no code kind of environment where users can just generate the certified codes, and based on MIL standard order standards, so those are available. This is the part that everyone does. This is the bottom of the V, where you do the design engineering, where you use high fidelity tools, where you use physics solvers, you do mechanical analysis, structural analysis, fluid analysis, electromagnetics analysis, the various different categories, optics, sound. So you have all these simulation tools where you do the study for the subsystem or a particular system within your whole product. The important part is how you validate whether this system is designed to meet your system level requirements. When all these system gets integrated, will they be meeting the system requirements? That's where you utilize techniques like reduced order modeling or surrogate modeling, and that's where you fuse your physics simulation with either the real data you have, the data from the products you have. You can fuse those and you can build up AI/ML fusion models. Once you have created these kind of reduced order models, these are models that are less computationally heavy, and you can run them quickly. Because you can run them quickly, you can integrate them together in a single environment, and then you can perform those model in loop, software in loop, hardware in loop kind of studies to validate your kind of system, and then you can perform a virtual verification and validation of your requirements, where certification question arise, okay, how can I validate my certification requirements? So this is how you can leverage these digital twin model of your individual subsystems, integrate into a larger system level model, and then perform the requirements verification and design validation studies. So there are several products, and what ANSYS believes in is not adopting any of these products all together from ANSYS. We believe in an open ecosystem. We have connectivity to all the other tools that are available in the market. So one of the product that allows, I'll be talking about that part. And to manage all this that was showcased in the previous presentation, you have a manager kind of where you can perform simulation process and data management activities, which activity will be performed in which sequence, and passing data to all those departments. So those kind of softwares on the enterprise level are available. What is important, as it was showcased earlier, that connection of your high-level system architecture models to your analytical workflow, that's where ANSYS ecosystem comes in. It's not just ANSYS system architecture modeler, that is SysML v2. As in previous session, it was talked about SysML-based technology, but SysML v1.x is something that industry is currently utilizing. SysML v2 is a modeling language that is being developed and will be finalized by the end of the year. So we have a modeler that is entirely based on the latest SysML v2. We do have connections with other system architecture modelers, be it from Dassault Systems, be it from IBM, be it from Capella open source. So we do have connectivity with those, where what it allows is to seamlessly pass on those data of your system as well as requirements, connect with the analytical workflow, run the analytical workflow iteratively, analyze various designs, perform requirements verification for various of those design cases, and bring back the qualified design cases for the further engineering. So this is the intention. I'll not go into the tool level, what kind of tool it is. It is a web-based tool. It allows you to collaborative environment, but it has connection with requirements management tool, functional safety analysis, embedded software, and you can connect with your analytical models, analytical workflow. So this is the main part that allows you to do that kind of study at the initial stage, and then go into the design of your design of your system, where you can build up those digital twin models post your simulation, physical simulations. So this is how you connect. You can perform, you can validate your requirements with a green tick or a red cross. It showcases in the single interface which requirements are being verified or satisfied. You can pass back those informations back to the system. You can perform trade studies. You can analyze designs. You can provide multiple objectives, and then you can pass back those design cases back to your system architecture model. So this, as I said, the build-up of analytical workflow involves multidisciplinary approach. You have to integrate various tool sets together. So the tool ANSYS ecosystem allows you to integrate be it your 0D, 1D tools like Excel, MATLAB, or be it Python scripts, be it any third-party tools on the simulation side, CAD tools. So we have ready-made plugins for majority of the tools, but this is a non-exhaustive set. We have integrated more than 250 plus tools together across the globe, and this kind of technology has been in use for past 25 years in North America, and this tool called as ANSYS Model Center Club with ANSYS SDK is something very prominently used in US defense accounts since past couple of decades. Another key thing is the capability to do the distributed engineering, where you can connect various disciplines together in a single workflow. So this environment allows you to connect to different disciplines in a single analytical workflow, and that's where you can rely on one team to do one analysis and another team to do another analysis and do an integrated study within a single environment. With the integration of tools, you have the advantage of performing iterative studies, and with iterative studies, you can do the design optimization, you can do probabilistic analysis, you can create reduced order models. That is the main part where you actually leverage these reduced order models of FMUs, functional mock-up units created for your software, into your digital twin model. So that's where it's very important. Now, going ahead, this was what I showed was on the conceptual level side, connecting your system architecture model to analytical workflow, making design decisions, and moving ahead. But this extends together to the extended stages where you do this requirements verification again for your detailed design, and that's where you then utilize your digital twin models and your system models, where you have reduced order models or a system level model where you perform system level requirements verification studies integrating various subsystems together. This is a framework that was talked for the certification. So we support various certifications and safety standards, that is ISO, MIL standards, ARP standards for aircraft. So those things, you have tools to perform safety analysis, and then you have tools to perform embedded software development. But what I'll be talking about is a customer story that highlights this process. Within, as current ecosystem, we have seen majority of the work that we do in our engineering is document based, whereas various set of data and models are exchanged across the disciplines, and there's a lack of digital thread. Because there's a lack of digital thread, there's lack of traceability, and there's lack of errors can creep in, and there is lack of efficiency. So to counter this, we came up with a framework. This is Northrop Grumman in the US that talks about a framework that talks about how you perform model-based system engineering, or how you perform engineering in an integrated model framework, where you have requirements, you have a SysML model, requirements translate into your system architecture model. Your system architecture model is then utilized to evaluate various design choices, connecting with the analytical workflow, where Model Center allows you to connect to various different tool sets, perform trait study, and do the requirements verification. And as and when the requirements gets updated, you can do this study and again, because this is knitted together in a single framework. So this is something that was talked about at initial stages. You might be utilizing very preliminary tools like MATLAB Excel, but as your design progresses, you will be integrating high fidelity tools like, be it on the electromagnetic side like HFSS, FICO, and then you integrate these, perform these studies, and then go on to the evaluation of your antenna-based design. This is a story of Northrop Grumman for antenna-based design. But this is one thing. Another is, that is a model-based system engineering approach. The another is how you connect different disciplines together in a single analytical workflow. So this is a story where for an aircraft, multiple different disciplines are engaged, and multiple different requirements are to be validated, and analysis has to be performed, be it mission level, be it operational, be it your simulation, aerodynamics, propulsion. So those things, how you can integrate them together in a single workflow. This is a study showcasing the single analytical workflow where each of those design disciplines are connected, and an integrated level study is performed where just change of your geometry of aircraft yields the performance results, yields the structural design analysis results, aero design results, mass and property calculations. So those things are done. In this video, you can see that your geometry is changing. This is a very accelerated video, and this is where reduced order models are utilized. This is where your digital twins for your subsystems are utilized, because you have to do the faster calculations. So with change of your geometry, you are able to see, you are able to arrive at your performance characteristics for the aircraft. So this is a study showcasing that. And why this is important, this is again Lockheed Martin doing the similar kind of study, talks about, because within an organization, if you want to do multiple design analysis, you have to set up it again and again, and that setup consumes a lot of time. With this integrated framework, with integration of tools and connecting into a model where you verify those requirements, you have to just set it up once and run the trades and perform that requirements verification through the trade study. So this is 2015 webinar. The work was done in 2009s, 2010s, and this tool and this particular ecosystem has been used for past couple of decades, for 20 years. So we have seen a lot of traction in India now. Majority of the labs we are in discussion with in aerospace industry are adopting this. They are going into the model-based system engineering approaches, going into digital transformation, adopting digital twin technology. So this is now being adopted widely in India as well. It's a start, but it's definitely that we'll be catching up soon. So that's it from my side. Any questions? Yeah.
It was a very exciting talk. Before we formally thank you, we would like to give you a token of appreciation. And to do the honors, may I please request Bashilia sir, Cluster Chair for Material Science Cluster, to the honors. So I think all the speakers have set the momentum very high for all of us to retrospect ourselves. Not retarding this momentum, we will go ahead with the valedictory session and then have the tea. So for taking over the proceedings, we request Sangeeta madam to please come on the dais.
Good evening to all of you. On behalf of Director NAL, I welcome you all for the valedictory session of the 1 week, 1 theme of AEISS at CSIR NAL. I invite Dr. Sridevi Jade, Director 4PI, Dr. Harish Barshilia, Cluster Chairman, and Dr. S.T. Aruna, Head DTS, to occupy the seats on the dais, please. Thank you all. I now request Dr. Harish Barshilia to summarize the 1 week, 1 theme events of AEISS theme.
I think everybody wants to go home. Anyway, it's my pleasant duty. Dr. Sridevi Jade, Director 4PI. Am I audible? Dr. Aruna, Head DTS, my industry participants, all senior colleagues from NAL, presenters, ladies and gentlemen. On behalf of Director CSIR NAL, I welcome you all to the closing session of the 3-day program of 1 week, 1 theme of aerospace, electronics, instrumentations and strategic sector theme at CSIR NAL. And I express my gratitude to all for participation in this memorable occasion. So I'll just give a brief background of the event. On June 24, 2024, Dr. Jitendra Singh, our Honorable Minister for Science and Technology, launched the 1 week, 1 theme campaign at Habitat Center in New Delhi to showcase the success stories of CSIR labs under various themes, which is built on the legacy and success of 1 week, 1 lab initiative. At NAL, we conducted 1 week, 1 lab events during 19 to 24th September 2023, and which was a grand success. Now, just to give you an idea that how the events unfolded, the inaugural session of 1 week, 1 theme of the AEISS theme was held during August 2nd to 4th, 2024 at CSR NPL, New Delhi, with participating laboratories, namely CSIO, CIRI, NPL, NAL, and IIP, bringing out the achievements in the theme in the area of electronics and instrumentation, mainly for the aerospace sector. The second event under the theme was conducted at IIMT Bhubaneswar during 12th to 13th of August 2024 with participating laboratories, namely NAL, NML, EMPRI, CGCRI, and SEMRI, while focusing on the aerospace technologies based on materials and mechanical systems for aircraft. The third and final event under the AEISS theme is just concluded at CSR and NAL with participation from NAL, CSR 4PI, SERC, CLRI, NCL, NGRI, and NIST, while focusing on civilian aircraft technologies. Now I'll briefly summarize the events which took place in the past 3 days. Of course, I'll not take much of the time because it will be simply repetition of what has been said by the various speakers. So to start with day 1, the program started with a keynote lecture by our director, Dr. Pashelkar, highlighting the vision and mission of various participating laboratories in the theme and their silent achievements in the area of aerospace-related technologies. Dr. Pashelkar also provided a glimpse of R&D focus areas catering to the needs of future aircraft programs of the country. In her opening remarks, Dr. Sridevi Jade, Director CSR 4PI, summarized various verticals which are being pursued by her laboratory and also CSR 4PI's contributions in the area of data science products across all themes of CSIR. She also emphasized the need of AI-enabled technologies and systems for various sectors, including aerospace. On behalf of Director Anil, I sincerely thank Madam for gracing the occasion on all 3 days. Director CSIO made a virtual opening remarks about CSIO's contributions in the area of head-up display and instrumentations for strategic and manufacturing sector in the country. Sri Jitendra J. Jadhav, Director ADA and Program Director Combat Aircraft, was the chief guest of the inaugural session and presented in detail about various ongoing programs in the country, including defense and civilian sectors. He also presented the future aircraft program, such as MCA and RTA. He explained that how close to 380 private industries in the country contributed to the success of LCA program, and also presented other enabling technologies, namely additive manufacturing and Industry 4.0, which need to be implemented in the manufacturing of aircraft. He invited the industries for the success of various national programs and also touched upon the policy support by the government for private players in these large aircraft programs. The guest of honor, Sri Subramaniam Ullal, highlighted the contributions of SASMOS in the aviation sector and also brought out the challenges faced by the small and medium scale industries while participating in national aerospace programs. In particular, he highlighted the need for quality control and assurance in the technologies being developed by private players in the country in the area of aerospace research. Following the inaugural session, the exhibition of various technologies developed by NAL and other participating laboratories was inaugurated by the chief guest at the Golden Jubilee Aircraft Hangar. In the afternoon session, a student visit and quiz program were conducted under the Jigyasa program, and approximately 80 students participated in this event. Day 2, Dr. Ashish Lile, Director NCL, was the chief guest for the inauguration of the technical sessions. In his address, Director NCL appreciated various major aircraft programs being undertaken by CSR NAL and assured that NAL and other national laboratories will contribute for the success of these programs. Following this, there were 6 presentations on aerial vehicles by program directors of HAPS, Saras Mark II, Hansa NG, and drones for solid waste management. Dr. C.M. Ananda, Program Director, Civil Aviation Program, presented a detailed overview of various past, present, and future aircraft programs of CSR NAL. A large number of industry participated in this session. In the next session, the project leaders from CSR NAL briefly summarized various indigenously developed technologies. This was followed by another session on aerospace materials and technologies which are being developed to support the aircraft program of CSR NAL. The afternoon session was designed for the contribution of other CSR laboratories in the area of AI-enabled technologies and systems, and also technologies for advanced devices. Day 3, which is today, the cluster chairman of various clusters, namely systems, materials, aerothermal, structural, aircraft clusters, they made brief presentations on NAL capabilities, facilities, and services under various clusters. The idea of this session was to facilitate modalities for mode of engagement with the industry for utilizing the competences, facilities, and services offered by CSR NAL and other participating laboratories. This session was followed by another interesting session on aircraft development ecosystem in the country by experts from various private and public sector aerospace giants such as Adani Defense and Aero and HAL. 2 detailed presentations were made by the representatives of HAL and Tata Elxsi. An NDA was signed with Tata Elxsi in the area of urban air mobility. The third session focused on Industry 4.0. Speakers from CMTI Bangalore and Siemens Bangalore elaborated on this interesting topic and presented the case studies of Industry 4.0 implementing at CMTI and Siemens. I just would like to mention here that this was the idea of our director, that he wanted to have this discussion during this theme. The last session of the day witnessed talks by subject experts from software giants. Just now we heard them, Siemens, Dassault, ANSYS, and Altair on digital twin technology and model-based systems engineering. Digital twin technology, as you know, it's a very upcoming technology, and if you can use that for the aircraft industry, that will be a great benefit. All the experienced speakers from these 4 software companies shared their experiences in the digital twins and showcased how to innovate, how the innovative solutions offered by their firms are helping the aerospace community. So just to give you a glimpse of what is the success of 1 week, 1 theme, I'm very happy to inform you that a great success was achieved during the last 3 days events, as more than 1,000 engineering students from different parts of the country, basically from the southern part of the country, 400 school students, close to 100 individuals in private capacity, and a record number of 90 industries participated in various programs during the 3-day events. The event was also represented by our sister laboratories, namely CSR 4PI, NCL, CMRI, NIST, NML, IMT, and CIRI. Further, there was a great mix of interaction between various CSR laboratories and public and defense sector PSUs involved in the aviation sector. We request the industry to provide suggestions for doing business in aviation industry so that the same recommendations will be submitted to CSIR headquarters for implementation and also evolve policies which are industry friendly. On behalf of Director CSIR NL, I thank all the participants, especially from the industry, for attending the event and making it a grand success. The take-home message of this event is that we need to work together as a family and make India the Vishwa Guru in aerospace sector. So now coming back to the way forward, we have been told by the CSIR headquarters that the similar engagements, events will take place next year with involvement of other scientific departments such as ISRO, DRDO and Atomic Energy in the form of 1 week, one integrated theme, that is OWIT. Finally, I'll request my industry friends to interact with our business development team who are present in this closing ceremony for various business-related queries and modes of engagement. I once again thank you all for participating in this memorable event. Jai Hind. Thank you.
Thank you, sir, for the brief summary of the OWOT events. I now invite Director of OPI to address on this occasion.
Good evening to Dr. Harsh Pashila, my colleague from CSIR NAL, Aruna, also my colleague from CSIR NAL, and both of them are heads of KTMD and DTS, and my colleagues from CSIR FOPI, head of the divisions, and from NAL, whoever is here, and industry participants. Good evening to all of you. I just now I heard Dr. Harsh Pashila saying that it was a big success. This is what OWOT was meant to be, is basically to emphasize on the I in CSIR, that is the industry part. Because in our name itself we have Council of Scientific and Industrial Research. So when I attended the inaugural event in Delhi in Indian Habitat Center, and our Honorable Minister Dr. Jitendra Singh very emphasized on that I. He said, see, he actually, last year he said, last year he realized when he was visiting CSIR labs that we are working in a very, 12 feet, inside 12 feet walls. Even the next door neighbor of ours do not know what we are doing. Like here, ISRO doesn't even know what we are doing. So it's like that. So like in other places, CSIR labs are close to, like in Hyderabad with Survey of India and all that. They are all in the same location, but then each one of them don't talk to each other. And also public didn't have awareness of what CSIR is doing. So he said we should go to public and create that awareness, and also with our neighbors, with whoever is interested. So that time he came out with 1 week, 1 lab. That is, all the 37 labs should do 1 week in a year, showcase what they are doing, and then show it to not only to general public, to PSUs, to stakeholders like Survey of India or whoever it is, like for you people, HAL, and also to the industries. So that is what happened. Then he realized we had a valedictory of the OWOL in Delhi. Then when he saw all the whatever events happened, there was a video played and all. Then he realized that it should be taken forward as 1 week, 1 theme, because CSIR has 8 themes. So there is an integration theme-wise with the industry. So this particular OWOT was to have theme-wise integration mainly with the industry. So this was focused on industry. So theme means that what happens is in CSIR there's so many labs belonging to each theme. So he said that all these labs should integrate and work with industry, so that the output of this event should be that we should have we should provide what industry needs. That is what is this thing, and also for both for the strategical sector and for societal needs. So this was the objective of OWOT. So this particular AEISS theme they conducted for aerospace electronic instrumentation. Earlier to that we had energy and energy devices theme. Then we'll have A&B, etc. So 4Pi being a data science, only data science lab of CSIR, we are a horizontal across all themes. So we participate in OWOT events of all the themes. So here we basically, as he had pointed out, we conducted a panel discussion yesterday on AI landscape of CSIR, where whoever is working in AI in CSIR, because in AI presence in CSIR is a maximum in 15 labs, whereas 37 labs are there. So this basically served as a platform not only to create awareness to the industry, but also within ourselves, that the whole of CSIR should be, we should have an AI-enabled CSIR. That is what was the final outcome of the panel discussion we had yesterday. And today, so yesterday we had given a brief of what is the AI landscape of CSIR, what was happening till date, what is happening now, and how to go forward in the future. So with that intention, we had this, and I do hope that it created the kind of impact which we expect from the industry, that we will know only as the time goes by. And even this OWOT event, see, when it comes to NAL, they already have a lot of industry sponsored projects, etc. So we can say this is a success, because most of the labs in NAL in this theme, whether it is CD Pilani, CSIO, NML, all of them have this kind of industry interaction quite well. So that way it was a success. So yesterday we also showed what we are proposing in the next year, that is AI 5.0 for industry, that is AI, CSIR AI initiative for industry. So we also got, we had proposed, we called industry meet, and then based on the problems that they are given, we proposed for a project where industry participation is around 40%, 50, I think 40 is CSIR, 20 is line ministries. So the proposal we have put for it, which NAL is also, almost all the labs, 34 labs of CSIR was part of it, where the focus was on what the industry, because each CSIR lab works in a very diverse areas, starting from a healthcare to, like, you have a CMAP, aromatic plants, and then Botanical Research Institute, and NEAST works in regional specific. So what is that in their area of expertise the industry needs, and then they went and spoke to the industry. Then we had a pan CSIR industry meet where I think around 50 industries participated, and then based on their input we have made this proposal. So it is a huge initiative, and I feel that it is actually part of what our Vice President envisaged for CSIR through this OWOT, but we have already done it before this theme. So yesterday we showcased that to the industry in case there are some more participants who want to participate. So that is how CSIR 4Pi has taken part, and along with CSIR 4Pi, almost 34 labs of CSIR also took part in this event, and I am glad to hear from Harsh Basila that it was a success. So that is a very good this thing, because this is the only theme which conducted over a period of 1 month, whereas all the themes are conducting only 1 week. Like 1 week means like parallelly they are doing, but this theme took August month and conducted not parallelly, separate events in each of the geographical locations of our country. So I'm glad to hear, and as he said, now next time I believe he is going to have an integrated 1 week integrated this thing, that is with ISRO, as all the ministries that are with our Vice President CSIR. So he wants all of them to integrate together and conduct. So that would be the next year, after seeing how this is. See, looking at the newspaper articles and what kind of progress we made, he assesses and then he gives the next what we are supposed to do, way forward for us. Basically, that I of CSIR has to be highlighted. That is his main goal. And we all being the employees of CSIR should work towards it, and we are working towards it. And with these few remarks, I would like to thank CSIR and NAL for giving me this opportunity, and also for conducting this session in this theme. Otherwise, we had to do it separately at 4pi. So it wouldn't have had that much impact it had when we do it with NAL here. So I thank one and all for the support. Thank you very much.
Thank you, madam. And we would like to have some feedback from the participants. So only industry participant available. 1 or 2. Press. Please. Yes.
Thank you, madam. Respected Sridevi madam, Maruna madam, Basil sir. So the reason why I'm here, I was so much fascinated about aerospace industry. Little bit about myself. I started about aerospace industry in '96 as a technician for Jaguar Aircraft. Just a self-motivated, did my engineering, and also I did my MBA from IIM Kozhikode. So to do something for aerospace industry, I started my own venture, Mayur Aerospace. To the feedback, so personally, would like to do something for India, some flight, compete with the global aerospace industry. So that is the intention. I would request to include participants for the programs like HANSA, RTA. Our competency, I spent almost a decade in US. Then I came back, started my venture. Please include us. I'm willing to do for NCNC basis also. Because once if I get the NAL tag on my company website, I can play like a bigger player to compete to the global ecosystems. That is the one intention, so please consider it, ma'am. Thank you very much.
Thank you, sir. Anyone else? So, yeah.
Good evening, ladies and gentlemen. Good evening, Dr. Harish. And Dr. Sridevi ma'am. And so I participated only today. I am Lieutenant Commander Madhav from Adani. Okay, from the user side, as a user in NAV, came back to the industry. The last 18 years I've been with the manufacturing industry. This, at least today, what I could see and what the goal of the organization in terms of interacting with the industries to take the technologies forward. This is what we also look forward. Though we are relatively new in the defense setup, just about 6 years old, we have already started manufacturing aircrafts. We have been delivering it to the customers. Now we want everything Atmanirbharta, we want to go towards that. So instead of starting from the scratch, we can take support from the respective labs so that the technology is manufacturable and taken to the customer in the right way. I think this is a good start of that, and we would like to have more and more interactions with the group so that the right exposure is there, that what are all the technologies available with the labs and how we can make it and productionizable one and deliverable one, rather than more like an research model and kept it in the shelves. Thank you very much, ma'am.
Thank you, sir. I now invite Dr. Okay. Yeah, please.
Good evening, everyone. My name is Shaktivel. I am from KRR Engineering Private Limited in Chennai. We are one of the TOT partners with NAL. And I have to say that NAL's culture has been super inspiring. It is some way, in a way, that culture has found its way into our organization. We've had a great run in completing some of the prestigious projects for many PSU plants. And also, there's a lot of upcoming projects that are in the pipeline. I'm happy to say that we just won another big autoclave from SAC Ahmedabad recently. And such programs, it definitely acts as a bridge, as a link between the industry and this scientific research institution. And whenever I come here, there's always a new set of ideas that keeps coming. So thank you for organizing such programs which acts as a bridge. So today we had a very, very fruitful discussions with Mr. Sridhara from PBMD. And we are also discussing on how we can get more technologies into the market and more products into the market. Thank you once again for the organizers of this event. Thank you.
Thank you, sir. I invite Dr. Aruna to propose the vote of thanks.
Respected dignitaries on the dais, of the dais, and my industry partner, participants, and my dear colleagues, as we draw curtains down for this 1 week, 1 theme event on the AESS theme, it's my great honor and privilege to propose the vote of thanks. First of all, I would like to thank our director, Dr. Abhay Pashilkar, for motivating and guiding and supporting us in organizing this event. In his absentia, I thank him for this support. Then I would like to thank Dr. Sridevi Jade, Director, CSIR 4PI, who was really one of the pillars for organizing these events, and she was there throughout the first day and the third day. And we had a session on the AI and ML related activities, and Madam has taken the initiative to organize that one session, and I thank Sridevi Jade for supporting us in this event. Thank you, Madam. I thank Dr. Harish Barshilia, Chairman, Cluster Chairman of Materials and Head Surface Engineering Division, for his summary of the 1 week, 1 theme event. Thank you, Dr. Harish. Before that, I just want to hand over a plan to Sridevi Jade, Madam. I forgot. Yeah. So I thank, I request Dr. Harish Barshilia to hand over the plan to Madam. I thank all our sister laboratory directors, like NCL director was present here and CSIO director joined us through a video. So I thank both of them for their support. I thank all the industry speakers and industry participants. Without their presence, this event would not have happened. I thank you all on behalf of CSIR NAL and all the participants. I again thank you. And I also thank all the TOT partners who are present, and all our CSIR lab speakers and participants from other CSIR labs like 4PI, NCL, NML, CMERI, NIST, IMMT, and CIRI. And I thank all the cluster chairmen and program directors who presented an overview of the activities of various clusters along with the facilities and the competencies of CSIR NAL. I thank all the industry speakers, particularly speakers from Adani Defense, VVDN, HAL, Tata Elxsi, CMTI, Siemens, Dassault, ANSYS, and Altair. All the technical divisions have played a key role in making this event a success. So I thank all the technical divisions, HODs, and the staff for their support. Similarly, all the service divisions are I acknowledge all the service divisions for their help. And foremost, I should thank all the active committee members of One Week, One Theme for striving hard to make this event a grand success. Thank you, one and all, once again. Thank you.
Thank you, Madam. We will conclude the program with the national anthem.
मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you all. I request all of you to have a cup of tea before you leave NAL. Thank you.